Hello everyone, I am Adrien Thibaud and I am a PhD student in the University of Toulouse. I work on congestion control in named data networking. Today I will speak about congestion control in NDN and in satellite network and about an enhancement of our proposition cooperative congestion control. In our study, we work with named data networking architecture, which is a content-based network. It offers multiple opportunities, such as multi-source and multipath retrieving. We will study this architecture in satellite networks, and more specifically, the congestion control. We will oppose Windows-based solutions to the new PACE-based solution we previously proposed. Here are the outlines of our presentation. I will now present concisely cooperative congestion control. Next, I will present evaluations of congestion control solution on satellite networks. Then I will explain the reactivity enhancements for our solution. And finally, I'll conclude the talk and present some perspective. Cooperative congestion control that we present at ICC this year is a PACE-based congestion control solution. It intends to distribute the flow on the network in order to fully use its capacities and propose some sort of fairness between the different flows. In our previous paper, we present the general architecture of CCC and the first and basic implementation. The architecture is divided in three main principles: cooperation between nodes, local supervision, and smart distribution. The modularity of our proposition resides in the 6 algorithms implementing our principles. The cooperation principle describes the exchanges of information that will be used by CCC. In the upstream, interest carries the objective of the flow. Initially, it corresponds to the targeted base of the consumer, but node in the network can split it on the different paths to the content. We define the conservation of the objective rules as follows. The sum of the outgoing objective is equal to the incoming objective. In the downstream, data carries the constraint for the flow. It corresponds to the maximum pace the interest of this flow should be transmitted on the link. Nodes in the network have here the job to aggregate the constraint coming from the multiple paths to the consumer. We define the aggregation of the constraints rule as follows. The outgoing constraint is smaller or equal to the sum of the incoming constraints. The equality here is not strict because of some local congestion event. The supervision principle is composed of 2 algorithms. The first one has the purpose to detect a problematic event, such as a congestion or a misuse of the capacity. The second one is here to trigger the right answer to this event. 2 answers are possible and are part of the distribution principle. They are the constraint reduction algorithm in case of a congestion event, and the constraint augmentation algorithm in case of a misuse of the capacity. Both these algorithms modify the outgoing constraint for all the active flow on the interfaces where the event occurs. Finally, there are 2 more algorithms in this last principle that focus on only one flow and its multiple paths to the content. The objective distribution algorithm decides how the incoming objective is split on these multiple paths, and the load balancing one decides the actual output pace of the interest. For the evaluations, we use the following topology. It is composed of 2 consumers, A and B, that want to reach different data through producers A1 and A2 for consumer A, and through producer B for consumer B. We presented 3 cases in the paper depending on the position of the satellite, but I will only present one of the cases here, the backbone case. It is a case where the satellite link is between R1 and R3 and where CCC shows the poorest performances. Due to this position, post the flow will suffer from the satellite delay, but only on one of the paths for consumer A. We compare CCC with two couples of existing solutions that we choose in our previous paper presented in last year's conference. They both combine a window-based congestion control solution and a forwarding strategy in order to use multiple paths. The top figure shows the rate of flow A, while the bottom figure shows the rate of flow B. As we can see, the two window-based solutions struggle to increase their respective rate. This is due to the AIMD mechanism of the congestion window that directly suffers of the long delay. The flow A still shows a faster increase with the Picon CS plus DRS solution because of the forwarding strategy that allows the flow to use both paths equally. The consumer is then able to increase its congestion window with the data collected from the non-satellite path. CCC suffers too of the satellite delay, but only during a relatively short convergence phase and only when flow B begins. When flow A begins, it is able to quickly reach the full capacity on both its paths. In addition to evaluate state-of-the-art solutions in satellite networks, we propose an enhancement of CCC that solves the convergence problem presented in the last figures. The problem comes from the implementation of the constraint decrease algorithm. Currently, when a congestion is detected by the supervision, it triggers a 10% decrease of the outgoing constraint of all the active flows. The first implementation of CCC set the new outgoing constraint to 90% of the measured incoming pace of the interest. But in this case, the notification takes one satellite delay to be applied and one other to be felt on the node that emits it. It induces a step-by-step resolution of the problem. Each step takes then a long time and the congestion issue is not immediately resolved. The enhancement we propose is to solve the problem in only one step. Indeed, when a congestion is detected, we now reset all outgoing constraints and trigger the constraint augmentation with all the capacity of the link. A new and correct distribution is then done as soon as the congestion is detected. As we will see in the results, it will still suffer the satellite delay, but only once. The figures here present the result of CCC with and without the enhancement. The left figures show the classical CCC performances, while the right ones show the new performances. Similarly as before, the top figures show the rate of the flow A and the bottom the rate of the flow B. The green curve shows the backbone case as before and is the one that is the most underperforming with the classical CCC. With the enhancement, the conversion phase is still visible, but only lasts one satellite round trip. The other cases are also improved and the conversion phase only lasts one terrestrial round trip. With our reactivity enhancement, the solution is able to reallocate the boundaries as soon as the congestion is detected. In conclusion, we study the behavior of window-based congestion algorithm and our solution cooperative congestion control on named data satellite networks. The window-based solutions are never able to increase the size of their window enough to reach the real available throughput. Besides that, CCC outperforms the other solutions regardless of satellite position in the topology. Its space-based approach shows few defects and allows the users to reach the maximum throughput. However, the hop-by-hop notifications of CCC come with a cost of a delay in the congestion resolution and is due to the way the congestion was first handled. We proposed an enhancement that allows CCC to increase its reactivity in such cases. Currently, our solution proposes a link-level fairness between the flows. In the future, we plan to achieve a network-level fairness while still use the network at its full capacity. Furthermore, one point that you might have noticed is that we only consider one incoming interfaces for the interest when there can be multiple. So we also plan to add this feature in our proposition in the near future. Thank you for watching my video, and I'll be pleased to answer your questions.